This is a brief lesson on finding and using Taylor series. And the main idea is that you don't always need to start from scratch, meaning starting from Taylor's formula to derive a Taylor series. Sometimes you can start with a given Taylor series and manipulate it. So you've actually maybe even done this before, but one thing you can do is use substitution. So if here's the Taylor series for e to the x, then if you wanted to know the Taylor series for e to the 2x, you can just take this series, and everywhere you have an x, you replace it with a 2x. It's just that easy. 1 plus 2x plus 2x quantity squared over 2 factorial, and so on. And then you can expand out and simplify if you want. Another thing you could do is use differentiation and integration to derive Taylor series. So suppose you knew that the Taylor series for 1 plus x expanded around 0 is x minus x squared over 2 plus x cubed over 3, and so on. And you want to know the series for 1 over 1 plus x. Well, you can recognize that 1 over 1 plus x is the derivative of natural log of 1 plus x. So its Taylor series will be the derivative of this Taylor series. So you take this thing, you differentiate, you get 1 minus x plus x squared minus x cubed, and so on. And it goes the opposite way too. You can sometimes also do integration of one Taylor series to obtain another one. Okay, you can also do multiplication. So for example, you could start with the Taylor series for cosine x. I've written it down here. If you wanted to know the Taylor series for x squared cosine x, rather than starting from scratch, you would just multiply everything by x squared. That's just multiplying by a power of x. You could also try multiplying two Taylor series themselves, although it gets very complicated keeping track of terms. I want to show you a few brief, cool applications of Taylor series. There are many, many, many applications. These are just a few. One is to figure out which function is bigger around a point. So let's take e to the t versus 1 over 1 minus t near t equals 0. So we're going to think of t as being very small, since we're looking near t equals 0. And we're going to expand e to the t. Taylor series turns out to be 1 plus t squared over 2 factorial, and so on. That exponential is one of the ones that it's good to know by heart. 1 over 1 minus t turns out to be 1 plus t squared, and so on. So you can compare these things. At lowest order, they're the same. They're both equal to 1. The next degree term is also equal. They're both t. The next degree term is t squared over 2 factorial for e to the t, and it's just t squared for this one. So this is bigger, right? You're not dividing by 2. And since we're thinking of t as small, the higher terms are even smaller things, cubes of t, quartic powers of t, and so on, that are very, very small. So we look at the smallest power where they differ. That's here, and since this one's bigger, it means this function is bigger near this point. So 1 over 1 minus t wins. We can also think about limits. You've learned a little bit about limits in this class, although we purposefully haven't been very formal about them. But we can ask, what's the limit as x goes to 0 of sine x minus x over x cubed? Well, you could try to make a graph, but even your computer program's got to figure out what the function is doing there. And the problem is that if you try to plug in x equals 0, you get 0 minus 0 over 0, and you can't divide by 0. So there's something kind of funny going on. And you could look at the Taylor expansion of this whole thing to try to figure out what that limit is. So let's do that quickly. We're just going to do our dividing by x cubed out in front. And then we're going to write down the Taylor series for sine of x. And then what we're going to do is just subtract our x at the end. So that's sine x minus x over x cubed. And what you can see is that this x term cancels out this x term. And if I divide everything else that's left by x cubed, I get minus 1 over 3 factorial plus x squared over 5 factorial, and so on with higher powers of x. And you can see that as x goes to 0, anything that still has an x in it goes away. And it's only this constant term in front, which is minus 1/6 that's left. That's the value of the limit. Here's another favorite example. Integrating when a function doesn't have an easy antiderivative or even any closed form antiderivative. So take integral from minus 1 to 1 of cosine of x squared. Normally what you would like to do is find the antiderivative of this function and evaluate at the endpoints and subtract using the fundamental theorem of calculus. However, cosine of x squared doesn't have an antiderivative, right? It's not something you can write down in a closed form. And by the way, this is called a Fresnel integral. It comes up in physics, and it's related to diffraction it's related to diffraction patterns. So what you can do is you can make an estimate for this thing, and there's no rule here, or no easy rule for how many terms to keep in your Taylor polynomial, but I'm going to take cosine of x squared, so that's 1 minus x squared squared over 2 factorial, plus x squared to the fourth of 4 factorial, and I'm going to stop there. And I'm going to anti-differentiate that and to try to integrate from minus 1 to 1. So the antiderivative is x. This becomes minus 1/10 x to the 5th. This becomes 1 over 216 x to the 9th power, and so on. And if I just take these three terms and evaluate from 1 to minus 1 and subtract, I get 1.809259. And the exact answer is 1.809048, and so on to many more decimal places. So you can see that just this kind of crude approximation, we matched to 3 decimal places. And I think that's a really cool way to get a quick approximate answer to this problem. Okay, there are many other important applications of Taylor series and Taylor polynomials, but these are a few, and thanks for listening.